Chapter 8 will look at the fourth quantum number and also look at trends that the periodic table can help us to predict just based on the position of the different elements. As always, there's some suggested problems for you that you can check your understanding at the end of the chapter. Quantum mechanics explains the behavior of electrons in atoms. And we've already discussed that we cannot pinpoint the exact position of our electrons, but we do know with high probability they exist in orbitals. And we give a description of where these electrons are found in the orbitals using an electron configuration. This is like an address that tells us where the electrons are in an atom. It's important because it helps to describe the behavior of the different atoms and also predicts properties that they have. When we're writing our description, we include the principal energy level. So that is the N value that we talked about in our solution to the Schrödinger equation. And that is represented by the first number in our electron configuration. The sublevel, this is our angular momentum quantum number, the lowercase l, and that is represented by the letter of the orbital in which the electron is found. And then we tell the number of electrons found in that orbital by putting a superscript. So this particular example says 1s1. Which element would this be? Well, it tells us we have one electron in the first row in the s orbital, so this would be hydrogen. There is one additional quantum number that we have not discussed yet, and that is our spin quantum number. We have discovered the spin quantum number by doing an experiment where we shoot a beam of silver atoms through a magnetic field. When that beam of silver atoms passes through the magnetic field, part of the beam is diverted up onto our detector, and part of the beam is diverted down. It splits into two. This has to do with the spin on our electrons. And so we designate this as a spin plus 1/2 or a spin minus 1/2. When we draw our electrons into the orbitals, we typically draw an empty orbital as a square or a line, and then we add electrons into it. So if there is one electron, we draw that one electron with a half arrow, and typically by convention, the first electron is spin up. So we draw it with a half arrow pointing up. If there are two electrons in an orbital, they have to have opposing spins. So one must be spin up and one must be spin down, or plus 1/2 and minus 1/2. The direction that the arrow is drawn represents the spin of the electron. If it's pointing up, we typically say that is plus 1/2. If it is pointing down, we say that is minus 1/2. There are certain rules we must follow in order to put the electrons into the orbitals. One of those rules is called the Pauli exclusion principle. This states that we cannot have two electrons in our atom that have the exact same 4 quantum numbers. every electron has to have a unique set of quantum numbers. This means that no orbital can have more than 2 electrons because in order to be unique, we have to have one with spin up and one with spin down. So knowing this and knowing the number of orbitals that are in a sublevel, this allows us to determine the maximum number of electrons in the sublevel. So in our s orbital, because there is only one possibility, and this is related to that magnetic spin number, m sub l. So for our s orbital, m sub l is only 0. We can have one orbital, which means a maximum of 2 electrons. In our p sublevel, our m sub l is -1, 0, and +1, which is 3 orbitals, or a maximum of 6 electrons. For d, -2, -1, 0, +1, or +2, 5 orbitals, maximum of 10 electrons, and for the f, go from -3, -2, -1, 0, 1, 2, and 3. These are the allowed values for the f sublevel. 7 total orbitals, 14 electrons. This relates to the length of each row. So our s orbital, there are 2 blocks for the s orbital, the 2 tall columns on the left side of the periodic table. The p orbital is the tall 6 columns on the right-hand side of the periodic table. The d is our transition metals, and there are 10 columns there. And the 14 electrons are the 2 rows that sit underneath the periodic table. So let's look at helium's electrons. We said that each electron has to have a unique set of quantum numbers. So helium has 2 electrons. They are both in the first energy level. So that means that both have the exact same n value. They are both in the s orbital. And so that means that they have the same L value. They are also in the same, they have the same angular momentum, magnetic quantum number, m sub l. So the only place where they have different quantum numbers is the spin quantum number, the m sub s. So our first electron, and just by convention, we usually say the first electron is spin up, +1/2. That means that our second electron has to be spin down, or -1/2. If we drew our orbital diagram, we would say this is the 1s orbital, and we would draw a half arrow pointing up and a half arrow pointing down. So just to recap, remember that the allowed quantum numbers are the principal quantum number with values from 1 to infinity, and this tells us the size and energy of the orbital, the distance we are from the nucleus. We have an angular momentum quantum number that tells us the shape of the orbital, and we typically relate these to letter values. So if L is 0, that is the s orbital, 1 is the p, 2 is the d, 3 is the f, and we can have values that go all the way up to n-1. Our magnetic quantum number can go from -L to +L, and this tells us the orientation in space of the orbital. And now we've added our 4th quantum number, which is m sub s. This is our spin quantum number. It can be -1/2 or +1/2 in value. There are only 2 possibilities, and it tells us the direction of the electron spin. Our orbitals with electrons, we've already talked about the Pauli exclusion principle that says that every electron has to have a unique set of quantum numbers. We also have a couple other rules that we need to follow. So one is that we always fill from the lowest energy to the highest energy. This is called the Aufbau principle, and that means we start with the s orbital. Once that's full, we move to the p. Once the p is full, then we go to the d, and finally the f, from lowest energy to highest energy. Orbitals that are in the same sublevel have the same energy. So all three of the p orbitals have the exact same energy as each other. All 5 of the d orbitals have the same energy as each other. We talked about the Pauli exclusion principle, so no more than 2 electrons per orbital. And then we have Hund's rule. Hund's rule says that when we're filling orbitals that have the same energy, we have to put 1 into each orbital before we start pairing them up. And this makes sense if you think about it, because our electrons are negatively charged and they are going to repel each other. So they're going to prefer to be in different orbitals before we begin pairing them.